Another day, another story. New data revises our view of this unusual supernova explosion. A team of scientists used NASA's James Webb Space Telescope to parse the composition of the Crab Nebula, a supernova remnant located 6,500 light-years away in the constellation Taurus. With the telescope's MIRI, mid-infrared instrument, and NIR-CAM, near-infrared camera, the team gathered data that is helping to clarify the Crab Nebula's history. The Crab Nebula is the result of a core collapse supernova from the death of a massive star. Welcome to Tabo Eminent Channel. The supernova explosion itself was seen on Earth in 1054 CE and was bright enough to view during the daytime. The much fainter remnant observed today is an expanding shell of gas and dust, and outflowing wind powered by a pulsar, a rapidly spinning and highly magnetized neutron star. The Crab Nebula is also highly unusual. Its atypical composition and very low explosion energy previously have been explained by an electron capture supernova, a rare type of explosion that arises from a star with a less evolved core made of oxygen, neon, and magnesium, rather than a more typical iron core. Now the Webb data widen the possible interpretations, said T. Temem, lead author of the study at Princeton University in New Jersey. The composition of the gas no longer requires an electron capture explosion, but could also be explained by a weak iron core collapse supernova. The Crab Nebula. An oval with complex structure extends from lower left to upper right against a black background. On the oval's exterior lie curtains of glowing yellow and green fluffy material. Its interior shell shows large-scale loops of mottled filaments of yellow, white and green, studded with clumps and knots. Translucent thin ribbons of smoky blue lie within the remnant's interior, brightest toward its center. The blue material follows different directions throughout, including sometimes sharply curving away from certain regions within the remnant. A faint, wispy ring of blue material encircles the very center of the nebula. Around and within the supernova remnant are many points of blue, green, purple, and white light. The James Webb Space Telescope's NIR-CAM, near-infrared camera, and MIRI, mid-infrared instrument, shows different structural details of the Crab Nebula. The supernova remnant is comprised of several different components, including doubly ionized sulfur, represented in green, warm dust, magenta, and synchrotron emission, blue. Yellow-white mottled filaments within the crab's interior represent areas where dust and doubly ionized sulfur coincide. The observations were taken as part of General Observer Program 1714. The Crab Nebula, also known as Messier 1, M1, is a supernova remnant located in the constellation Taurus. Its origins trace back to a stellar explosion that was observed by astronomers on Earth in the year 1054 AD. Supernova Explosion. The Crab Nebula was formed from the explosion of a massive star in a supernova event. The supernova was observed on Earth in 1054 AD by Chinese and Japanese astronomers, and potentially by Native American tribes. The supernova was so bright that it was visible during the daytime for several weeks. Studying the present to understand the past. Past research efforts have calculated the total kinetic energy of the explosion based on the quantity and velocities of the present-day ejecta. Astronomers deduced that the nature of the explosion was one of relatively low energy, less than 1/10 that of a normal supernova, and the progenitor star's mass was in the range of 8 to 10 solar masses, teetering on the thin line between stars that experience a violent supernova death and those that do not. However, inconsistencies exist between the electron capture supernova theory and observations of the crab, particularly the observed rapid motion of the pulsar. In recent years, astronomers have also improved their understanding of iron core collapse supernovae. Webb measurements reconcile historic results. To lower the level of uncertainty surrounding the crab's progenitor star and nature of the explosion, the team led by Temem used Webb's spectroscopic capabilities to hone in on two areas located within the crab's inner filaments. Theories predict that because of the different chemical composition of the core in an electron capture supernova, the nickel to iron, Ni-Fe, abundance ratio should be much higher than the ratio measured in our Sun, which contains these elements from previous generations of stars. Studies in the late 1980s and early 1990s measured the Ni-Fe ratio within the crab using optical and near-infrared data and noted a high Ni-Fe abundance ratio that seemed to favor the electron capture supernova scenario. The Webb telescope, with its sensitive infrared capabilities, is now advancing Crab Nebula research. The team used MIRI's spectroscopic abilities to measure the nickel and iron emission lines, resulting in a more reliable estimate of the Ni-Fe abundance ratio. They found that the ratio was still elevated compared to the Sun, but only modestly. The revised values are consistent with electron capture, but do not rule out an iron core collapse explosion from a similarly low-mass star. Higher energy explosions from higher-mass stars are expected to produce ratios closer to solar abundances. Further observational and theoretical work will be needed to distinguish between these two possibilities. At present, the spectral data from Webb covers two small regions of the crab, so it's important to study much more of the remnant and identify any spatial variations, said Martin Laming of the Naval Research Laboratory in Washington and a co-author of the paper. Crab Nebula Deconstructed. This video shows the different major components that compose the Crab Nebula as observed by the James Webb Space Telescope. Despite decades of study, this supernova remnant continues to puzzle astronomers as they seek to understand what kind of progenitor star and explosion produced this dynamic environment. Mapping the crab's current state. Besides pulling spectral data from two small regions of the Crab Nebula's interior to measure the abundance ratio, the telescope also observed the remnant's broader environment to understand details of the synchrotron emission and the dust distribution. The images and data collected by MIRI enabled the team to isolate the dust emission within the crab and map it in high resolution for the first time. By mapping the warm dust emission with Webb, and even combining it with the Herschel Space Observatory's data on cooler dust grains, the team created a well-rounded picture of the dust distribution. The outermost filaments contain relatively warmer dust, while cooler grains are prevalent near the center. Where dust is seen in the crab is interesting because it differs from other supernova remnants, like Cassiopeia A and Supernova 1987A, said Nathan Smith of the Stewart Observatory at the University of Arizona and a co-author of the paper. In those objects, the dust is in the very center. In the crab, the dust is found in the dense filaments of the outer shell. The Crab Nebula lives up to a tradition in astronomy. The nearest, brightest, and best-studied objects tend to be bizarre. These findings have been accepted for publication in the astrophysical journal Letters. The observations were taken as part of General Observer Program 1714. The James Webb Space Telescope is the world's premier space science observatory. Webb is solving mysteries in our solar system, looking beyond to distant worlds around other stars, and probing the mysterious structures and origins of our universe and our place in it. Webb is an international program led by NASA with its partners, ESA, European Space Agency, and CSA, Canadian Space Agency. Thanks for watching. Request you to subscribe the channel.